Hello everyone and welcome to our next session of our Digital V-Days. I'm very happy to welcome today Ronald Stärz. Welcome, Ronald.
Thank you very much for the kind welcome.
Yeah, so today's topic is about Infineon's Robotic Development Platform, IMR, Experiment, Innovate and Accelerate. So I'm very interested in the topic I'm looking forward to it. And I'm very happy also to welcome all of you. So very nice that you took the time to participate. Some more information from my side. You will be muted during this webinar, but you can ask us all your questions in the chat. You find that on the right-hand side. So you will also then, later on after the presentation, we will go through the questions. There we have some time scheduled, and if we can't answer all your questions today, then we will answer them later on via email. And if you have any other questions, then just email us. Also then at the end of the webinar, we will also share the slides with you. And I think that's enough from my side. Then I wish you an exciting webinar. Have fun, and stage is yours.
Thank you very much. Thank you all for participating. Just a short introduction from my side. My name, Ronald Stärz. I'm leading the System Competence Center at Power Semiconductors and Sensors within Infineon. Our department is located in Innsbruck, Austria. And today I would like to give you some insights into the idea behind the IMR that we call the robotic platform, and some details about some functional blocks which may be or hopefully will be of interest for you. So let's dig into what we have presented for you. So I will go into this ideation behind the concept of the robot platform, give you some details on the system, and then, as mentioned, step into several functional blocks. And at the end of the presentation, I would like to guide you a little bit into the ecosystem, which may give you some more access to detailed information and how to proceed in the case you would like to either build your own robot or take it as it is for your further investigations. So the idea behind realizing such a system was not that Infineon ever wants to build robots, but giving a broad audience the possibility to use predefined functional blocks, prefabricated functional blocks, and having such a foundation, so to say, where you can combine those functional blocks, which at the beginning looks like a robot, but is not a real robot as a robot company would build a robot. And this, of course, incorporates a lot of different products from Infineon and showcases different approaches to system solutions in different areas of the functionality. And one main aspect of the platform is to establish this as a collaborational platform, especially for universities and high schools, giving a basis for further, let's say, scientific approaches, or on the technical side, to step into your own developments in the, let's say, global topic of robotics. And what we also wanted to realize is some sort of one-stop point where you can gain all the information that you need once you ever want to step into the topic of robotics and build your robotics. And this, of course, is accompanied by the according software ecosystem, not just one. We do have some more ecosystems that we will show a little bit later. So, stepping back, so when we switch back in time We are in, let's say, April 2023, where the idea was born to realize such a platform and what has a robot to do with a semiconductor company. And what you can see here on the top left-hand side is a so-called wafer shipment container, where normally the wafers are shipped worldwide. And stacking such wafer boxes then gives a three-dimensional structure, which the first concept led to, let's say, the full 3D model of a robotic vehicle. This was a little bit refined then, and finally this is the current solution, which incorporates different functional blocks. Like, okay, we do have some structural elements like the mechanical platform where all is built on. We do have the wheels and plates out of which the robot is set up. We do have motor control and the drivetrain, power distribution system, batteries and the according battery management system, different versions for the main control of such a robot, and of course a lot of different variants for the sensors that can be used in such robotic applications. So this is the high-level view on the system. Now I can give you some more details, and first stepping into the block diagram of the system. As mentioned previously, we do have some more insights on the functional blocks. What you can see here, we do have this battery management systems. So this was a necessity to realize this in a redundant way and allow hot swapping of battery packs. We do have 4 times motor control. We do have the main controller, which allows the interaction either from outside or autonomously. And sensor in the current version is done by time of flight sensors, power distribution, redundant as well. And for, let's say, the indication of, let's say, fancy lighting effects, we have designed those LED boards which are mounted on the robot, but easily can be interchanged to any other functionality. So, and out of this block diagram, then it comes to real hardware, and one of the, let's say, base layers of this system is a simple motherboard, as you may call it, where you can see that we have a lot of connectivity on this motherboard, and we do have this slot system where those individual functional blocks then can be plugged in to form the full system that we have realized. One of those first functional blocks is the main control. This is a very, let's say, simple realization of the main control. Basically, it deals with some external commands, either given by the CAN communication or by some remote control, calculates the speed vectors and then transfers these speed commands to the individual motor control boards, which then, of course, turn the motors accordingly. Motor control itself is based on a system in package, which is called the IMD 701. So this incorporates a microcontroller as well as the gate driver, which then via the external power switches is directed to the motor which is connected to the system. In reality, this then looks like this. We do have this motor control board with the IMD 701, the 6 MOSFETs which form those 3 half bridges to deal with the three-phase brushless DC motors. In the current version, this is a sensored field-oriented control implemented. Therefore, we rely on a magnetic angle sensor, which in the robot is mounted directly onto the shaft of the wheel. And this motor control then is part of one of the first ecosystems which I would like to mention, which is the so-called Robotics motor control workbench. So this is a standardized graphically user interface which allows you to select out of different versions of motor control, like you say block accommodation or trapezoidal or field-oriented control based on different hardware topologies in terms of either using sensored or sensorless algorithms dealing with, let's say, single shunt, two shunt, three shunt versions, or the censored versions with incremental or absolute encoders which can be mounted. And all those details which are needed to set up the encoding signals at the gate driver, all those parameters can be defined via this user interface and then be transferred into the EEPROM of the controller itself. And then you have a standalone system which turns your motor and let you communicate with the outside world via different variants of interfaces. The next functional block which I would like to mention is the battery management system. Battery management system is based on a cell pack of 12S with an according analog front end. This front end deals with all the measurements which are necessary for cell balancing and cell health monitoring, like cell voltage measurement, different temperature measurements at different positions of the overall system. We do have the safety switches. So there we have the main safety switches, and in parallel we do have the pre-charge switches. Those are controlled via the high side gate driver, the 2ED4820, which is connected via SPI to a microcontroller board, and this microcontroller board incorporates an e-paper display, which I will show you then on the next slide, which nicely allows to monitor the current state of charge, state of health, and the individual parameters of the individual cells during runtime. And of course, we do have the communication via CAN bus to the overall system. Last part to mention is the current measurement. Current measurement is done redundant, one hand side shunt-based, for being able to safely control the safety switches in a direct way without any software incorporated. So for example, overcurrent detection or short circuit protection, and on the other hand side, TLE 4972, which allows then high resolution current measurement, which is a necessity for the determination of state of charge, state of health of the battery, first level done by Coulomb counting. At the end, the system looks like this. So we do have two boards. One is the power board, which incorporates all those safety switches, current measurement, and analog front end, and the battery holders. And on top of this power board, there we see this piggyback board mounted with this e-paper display that I previously have been mentioning, with the individual details of the cell. This all is incorporated in a coding housing, which makes the interchangeability on the robot very, very easy. So we do have hot swap functionality as well. So once one of those battery packs is empty, it automatically swaps to the second one. You remove the discharged one and place it into the charging station. Charging then itself is controlled by the system on its own as well. Next important block of such a system is the so-called power distribution, so which not only generates the different supply voltages of the different functional blocks, but also allows to monitor the current consumption of each of the different loads which are connected via this previously seen motherboard. And therefore, this also gives you the opportunity to step into some deeper, let's say, energy analysis of such a robotic system to estimate, calculate, observe the power demands of a certain functional block, let it be a sensor or some sort of actor, and you have a high resolution measurement of the power draw of the system. The system itself is based on a synchronous buck at the first stage, and then a 4-phase interleaved buck stage, which then transfers to a power rail with 6 outputs, and those outputs can be switched individually. So in case you are in a mode where you have to save power on your system, you may switch off 1, 2, 3, 4, 5 of the functional blocks of the robot, which are not essentially needed, for example, to come back to the home base for being recharged, for example. Okay, this then looks like this. As mentioned previously, we do have the the synchronous buck here. We do have the 4-phase interleaved buck controller, then with the 4 individual outputs connected to the power rail, and then we have those 6 outputs which are monitored independently. The last functional block which I would like to dig a little bit deeper is the time of flight sensor. In our case, this is a so-called HTOF or hybrid TOF sensor. Why this? Because this device offers 2 different ways of operation. On one hand side, we do have this flood illumination, which gives you, as mentioned here, those 20,000 points in 3D in a certain field of view. Okay. Accuracy resolution is always depending on the distance to the according target or obstacle which is in the field of view. One hand side, and on the other hand side, you also can do spot illumination, which reduces the number of data points to 600, but gives you more detailed insight into the real shape of your surroundings. So for example, for some sort of edge detection, this spot illumination is the preferred solution for being able to detect some certain angles, or for example, the height under a certain furniture where you will have to move you to with your robotic vacuum cleaner. Then this data from the HTOF sensor is processed on a dedicated control system. This can be different versions which can be used there to determine the slam, do the obstacle avoidance, could be Qualcomm RB5, for example. It could be a Jetson Nano, could be a Raspberry Pi, and any other, let's say, possibilities that you know of, or could be a suitable platform. Currently, this all is implemented in ROS, and therefore you need some system on which you can run Ubuntu in the needed version for being able to run ROS. Okay, then I will conclude with the functional blocks of the platform itself and lead over to the data community, so to say, that we have built up. So the first entry into more detailed information on the robot system can be given by infineon.com/IMR. There you are led to this landing page, and this landing page allows you to select out of 3 variants. Either if you are a beginner in robotics, or somewhat experienced, or you are an absolute expert. Depending on the selection you do here, you will be guided to different other pages then, which deals with more and more detailed information down to the silicon or GaN technology, which is used in several devices. And a very nice thing at this page is this 3D interactive model that we have of the robot. And for example, if you hover over this model, you can step down, look into the details of the platform, and once you have selected the detail that you are interested in, you can directly select, okay, I'm interested in the motor control solution, and then you are guided to the dedicated motor control page with all the user guides, user manuals, which explain the hard and software which is implemented on this functional block at the moment. And another landing point for interaction on the topic is the Infineon developer community, where we do have a dedicated section for robotics. And so please, if you do have any questions, any ideas, any necessities, then please, if you have not done so already, register at My Infineon, and you will have access to this developer community page, where your questions then are guided to the according application engineers, and they are all happy to support in finding a solution for you. Thank you very much. This was it from my side, and I'm looking forward to the eventual questions that you may have. Thank you.
Yeah, so we have to say thank you, Ronald. Thank you very much for the interesting presentation.
Welcome.
And yeah, as you already said, now we have the time to go into your questions. So if you have any questions, then just chat us, and yeah, we will go through them. We are heading right into the first questions. Ronald, first question here. You've been mentioning the three phase, thank you, BLDC motors are used in IMR. Can we use other types of motors as well?
Okay, yes, of course you can. So in terms of hardware concept design of the motherboard that you have seen, and the slot system that we provide, you have the opportunity to either use brush DC motors, you can use three-phase brushless DC motors, but you also can use stepper motors. Stepper motors are currently not supported with the hardware that we have on board, so this would require a dedicated design of the according motor control board. But in principle, if, for example, you do have a finished motor control for stepper motors, this can be implemented in the overall system as well.
Okay, thank you very much for that answer. Then next question here. If we want to integrate our own sensor device into a system, how can we proceed?
Okay, so for example, if you would like to deal with a radar sensor to do some, let's say, edge detection to disallow the robot driving into the pool which you have in the garden.
Oh, okay, yeah, that pool, I would like.
Would like to avoid this. So the backbone of the robot is the CAN bus for the communication. So on one hand side, you have to meet the requirements of the CAN bus and define your own CAN IDs within the overall system. Then you can communicate with all the functional blocks. So this is from a communication level. From the power supply level, we do offer either direct DC supply from the battery. So this may vary in, let's say, the range of 32 to 48 volts. Then you can deal with this power supply and make your own PMIC on the board eventually. But if 5 volt would be sufficient for your sensor device directly, those are available. And in terms of mechanics, so the robot itself, you do not need any tools to mount or dismount all the boards which are on the robot. Your 2 fingers are enough because it's all just hand mounted, and you easily can interchange those individual boards which are on the robot.
Very flexible then.
Yeah, and furthermore, exactly, almost forgot it, all the templates for the communication interface that they have, the form factors of the different boards which are on the robot, all those will be provided on our robots community page.
Very cool. Okay. Well, thank you very much for that answer. Then we have a look at the next questions here. Do you have any reference cost information for these functional blocks?
Yes and no. So we are currently in the phase of stocking those boards in our internal warehouse, and those boards will be available then via our web page. And then you also will find the pricing information there. So please be patient. May take some weeks till the information is given there, but all the functional blocks of the robot will be available via the Infineon website for direct purchase.
So everything also brand new here?
Absolutely new, yeah.
Okay. So then I see one more question for now. Where can I find the documentation, and is there a possibility to get some example code?
Okay. Yes. So documentation, as mentioned previously, like the user manuals, they are online already and accessible via the infineon.com/IMR site. Example code will be provided in different ways. We are currently in the phase of transferring this code into the example code section of the Modus Toolbox. So Modus Toolbox is the software IDE which is needed for our microcontrollers, and within the next release, most probably all the code which currently is running on the IMR then is accessible out of Modus Toolbox in the example code section. If you do have a very urgent project and need initial support, then please contact us directly, and we will try to help you in a very short time frame.
Okay, Ronald, thank you very much for that answers. Okay, there is one more question I see right now. Will be your reference designs open source?
Yes, of course. So the whole robot system is open source then in hard and software, and the sooner or later you will find all mechanical part drawings and templates for each individual PCB. So this is done in Altium. So if you can directly use Altium project or can import Altium projects, those then are freely available for reuse on your site.
Okay. Then I think we are already done with our webinar. Thank you very much for your attention, and a big thank you to you, Ronald, for your presentation and all the answers.
Thank you very much. It was a pleasure being here.
Yeah, it was a pleasure to have you. So then, stay tuned. We have, I think, 3 more sessions today coming up. So stay tuned. Maybe there's also something more interesting or another interesting topic also there for you. And then I would say thank you very much and have a nice day. Goodbye.
Thank you. Bye.